Okay, thank you very much for coming. I have like 1 hour, 15 minutes, and we are going to start with a topic which is one of the hot topics in power systems. How many of you is aware of the meaning of the unit commitment, of the term? Okay, 1, 2, 3. Okay, this is a classical problem, and we like to start this course presenting models for this issue because we think that is a good way to enter into the complexity that decisions that are made in power systems involve, right? Okay, so the purpose of this session is to introduce you once in the, let's say, the theoretical concepts, but I want you to start playing with a prototype. We have prepared a couple of prototypes. Due to the snow, and we had to condense the course in only 4 days, not 5. I'm going in principle to use just one single prototype that you can play with without having to install nothing in your computers. We made an effort trying to use Google Colab, as you saw by emails of Pablo, okay? So with only following my instructions, I think that if we do it, you will be able to run a mock-up, a prototype that will help you to understand all the related concepts, okay? So before doing that, a few words. What is the unit commitment? Okay, well, the unit commitment is a classical problem in the power systems operations related to the short-term planning. Unit commitment means that you need to decide which units to start up and which units to shut down. Why? Because producing electricity is not something that you can just do as you want. You need to follow many technical constraints, especially when you had thermal power plants. Deciding to start up one unit takes several hours. It's a process that cannot be done automatically. And once that you start, you cannot shut it down immediately. You need to be a number of hours. The maximum gradient of the variation of power between consecutive hours is very limited. So it's a process that involves discrete decisions, okay? So what is the objective? The objective is to be able to find the optimal scheduling of all my generators in order to minimize a given objective function. In general, the total operational cost, okay? But we want to minimize the total operational cost, so this would be the objective function that Pablo mentioned before. In our case, would be to minimize the total operational cost. In the short term, 1 day, 2 days, 1 week, 2 weeks, subject to meet the demand for the electricity in every hour, but also without violating all the technical constraints that we have in the system. Can you give me an example of technical constraint that an operator may face? Wind is not always available. We cannot produce as much as we can. So that would be a capacity limit, okay, in the sense that we cannot produce more than what we have available. That's a good point. Any other example? Strange weather conditions. Okay, this might affect the availability of several generators, several lines. So maybe you want to transmit power through certain power lines that are not available, and this needs to be taken into account in what is called a transmission constraint unit commitment. Okay, very good.
Electricity demand.
Yeah, the demand is, but the demand is, let's say, the most important constraint that we have in our system. We want to minimize the total operational cost, subject, first of all, to satisfy the demand. Otherwise, we don't have the problem. I mean, we build the whole power system to satisfy the demand. This would be the first constraint, okay? But from the technical point of view, there are other constraints that affect individual generators, for instance, and this is particularly tricky, is that maintenance schedule. This is something that you have to incorporate in your operation decisions. But here we see that somehow we need to take into account medium or long-term signals into our short-term operation, right? We want to operate. What is the difference between operation and planning and expansion? In the expansion planning, you need to decide investments in new generators ahead, several years ahead. In the operation, we have certain assets, and we need to make the optimal decisions to operate them in order to fulfill certain objectives, okay? This is an operation problem, but we need to incorporate somehow signals from the higher hierarchy models. Somebody has to tell me which units are available because they are not carrying out maintenance, or how much water I can used this week and cannot be used because otherwise it's going to be needed in the future. Okay, so among all the technical constraints that affect the generators, one very important is the minimum stable load, which means that once that you connect the generator, it cannot produce between 0 and the maximum capacity freely. It's like either I'm off, or if I'm connected, at least I need to produce at a certain level. Okay, this minimum stable load. This, from the optimization point of view, is a hard issue because it's like, either I'm off, or if I'm on, I need to produce above certain level of power, and then we have a range. So this illustrates the need of using binary variables. This is why the unit commitment is a hard problem, because it involves discrete decisions that are either yes or no. Either I start up the unit or not. I cannot start a unit 70% because physically that's not possible, you see? And making optimization problems with binary variables is even harder than when we have continuous variables as in the example of Pablo. Okay, but apart from all the technical constraints, we need to take into account as well some other constraints that can be non-technical, but for instance, regulatory constraints, like you cannot emit more than this amount of CO2, or everything that you can imagine. We can put constraints in our optimization model in order to obtain a solution that satisfies not only the pure economical criteria, but other criteria that might be driven by energy policy, etc. So we will obtain the physical operation. Strictly speaking, the unit commitment is start up or shut down. But in order to obtain that decisions, we also obtain an hourly scheduling. How much, what is the dispatch of every generator in every hour, or nowadays, for instance, in Spain, the market is cleared every 15 minutes. So it's not necessarily 1 hour. It can be done in shorter time periods, okay? And this also will allow us to obtain a forecast of the total operational cost and the marginal costs. Okay, and why I'm explaining that? Well, this is just an example of, as Andres mentioned in the introduction, at IAT we worked in a close collaboration with the industry. Okay, so we developed models for making real decisions in the utilities. In my case, I've been leading some projects. Endesa is like the second largest utility in Spain, and the models that they use in their daily operation in order to plan the operation of all their portfolio, hydrothermal, and how to convert these decisions into bids into the market, and how they, learn from the market, and how they incorporate all this information is by means of these models, okay? In the case of XCOM, is the unit commitment model that we have developed for them, of course, adapted to a market environment where they don't want to minimize the total operational cost. They are an agent playing in the market, and therefore they have other kind of objective constraints, objective functions, like trying to maximize the revenues, the profits. This is an idea of the size that Endesa has, with a very diverse portfolio. They have combined cycle power plants. They have hydro units, more than 260 hydro turbines, okay, with very different sizes, with more than 80 reservoirs. And we need to optimize all these elements, all these units, in order to obtain a operation that is feasible, which means that it can be put in practice. I need to obtain hourly schedules that can be realistic, okay? And this is done in a, let's say, digitalization environment, where all these models are not run in the servers of the company or in the computers. They are run in the cloud. They are using Amazon Web Services. There are other possibilities. So our goal here is to design the optimization models. Somebody is trying to feed all the data, all these databases in the big data. Every day they have to update what are the prices of the fuel, what is the level of my reservoirs, what is the forecast of the demand. They need to update that on a continuous basis. We run the models, okay, and the users can make at the end decisions based on that results. Okay, so why is the unit commitment let's say, a classical problem? Well, first of all, a bad management of the resources. I mean, improving 1% the quality of the objective function means a lot of money, and therefore, I mean, it deserves not to rely on a, let's say, a good enough solution. I mean, improving the solution it can have a big impact on from the economic point of view. And from the mathematical point of view, it has several characteristics that makes this problem very interesting from the theoretical point of view. Why? Because the objective function might be non-convex. Optimizing non-convex functions is challenging from the mathematical point of view, and especially because it has binary variables related to all these discrete decisions that I mentioned before. Okay, and this is, well, a consequence of the mix of available generators that we have, and each one of these technologies subject to different different constraints that need to be modeled. So imagine that you have only 2 hours and 2 units, just a simple, let's say, a scenario. Which are all the possible combinations? Well, 2 to the power of the product of number of hours and number of generators. So imagine only with 2 hours and 2 units, the possible combinations, one is on in the first hour, the other is not. I mean, if we want to explore all the possible solutions by enumerating all the let's say, theoretical combinations, that's impossible, because you may have, imagine a problem with 168 hours in a week and with 100 generators. This is 2 to the power, I mean, it's a huge number. So this is why we rely on mathematical programming. Is this an old-fashioned problem? Not at all. The unit commitment is on the agenda. This is the FERC web page, where you can see that every year they organize different conferences in order to improve the operational efficiency of all the software used to operate the system. The unit commitment was last year conference. I mean, there is a big interest in the power sector. Whenever there is an advance in the computer capability or in the theoretical developments, okay, a lot of problems related to the power sector can be benefited, and they're always pushing towards having a more efficient operation. Okay, how do we do that? Well, now I'm going to be a little bit fast because I want to start playing with the prototype. But obviously, the power that we produce with a generator is a continuous variable. I mean, along the time, right? But in order to plan the operation, we need to discretize the time in discrete time intervals. Period 1, period 2, period. For instance, if we have hourly periods in 1 week, we may have 168 hourly periods, okay? Some of these variables might represent an average value in that hour. Some others might represent an instantaneous value of this variable. For instance, when you are modeling the reserves in a reservoir, the amount of water that you have, either expressed in terms of energy or either expressed in terms of cubic meter of water, it's what is the instantaneous volume of water at the end or at the beginning of the period, okay? You see what I mean? It's like an instantaneous value. However, if you're talking about the energy production, this might be the average value of this variable in the period. Okay, so for instance here, if you have a whole week, we are representing, as you can see here, something which is continuous, like the red curve, by means of a discrete value every hour. And I said it, which is obvious, because sometimes you might get confused in interpreting the results if you don't know exactly what is the physical meaning of every variable that you have as modelers. As when you develop your own model, you need to be very aware of the meaning of each variable. Okay, today, as it's the intro, we are not going to model the network. The network will be explained tomorrow. Tomorrow we are going to see how the network, how the existence of lines condition the operation that we can have from a physical point of view. Because as we will see tomorrow, I mean, moving electric power through the electric grid is not as if we had highways where we can redirect the flows of power as we want. I mean, the flows of power, flow according to the Kirchhoff laws, and we have less freedom to redirect them as we want. So this is something that we will see tomorrow. Today, now I'm going to do a single node approach, which means that we are going to optimize this unit commitment as if all the generators were injecting power in one single node without modeling the network constraints. You see what I mean? So it's like we have, of course, the demand is the end user's demand, residential or industrial. We need to add the estimated losses, because this is power that somebody has to produce, the losses that we have when we are moving power through the lines. These losses that are lost due to the Joule effect, somebody has to produce it. So it's like we have the total load here that we draw power from this single node, okay? Also, if we are in a system that we are exporting, this is an extra demand, and if we have pumped storage power plants, well, we are extracting power from this single node, right? It's a consumption, it's demand of power. Who is injecting power? The generators, okay? Either thermal, hydro generators, nuclear, or renewables. Sometimes you can see in the textbooks that we distinguish between gross generation and net generation. Why? Because whenever you whenever you produce power with a power plant, part of its consumption goes back to the power plant to feed all the auxiliary services that it has, I mean, moving the belts, everything, okay? So at the end, what you have is like the net generation is only a fraction, maybe 96, 97% of the actual generation, okay? But when you are optimizing the total cost, and this is why we need to take that into account, okay? So we have all the generators putting power here, and then we have imports and renewables, okay? This is what we have. And we need, in this case, what is the demand that we need to satisfy every hour? This is an input data. Somebody has to tell me what is the demand that every hour I need to satisfy. Do you think that this is realistic? Do we know now, 1 week in advance, what is going to be the demand for the next week? Exactly. Well, that's not possible, okay? We are going to do that assumption in this model here now. In the second part, Andres will provide you some material to see how can we make decisions when these kind of variables are uncertain. So if you have uncertainty in terms of the total demand or the wind production, so this is what we call a deterministic approach. It's like if we had a crystal ball where we know everything. Well, this is the first model, so we have to start with the simple approach, right? Okay, so typically somebody in the statistical department where they are applying sophisticated methods, statistical and forecasting methods, tells me, okay, this is the demand for the whole week. But apart from being able to satisfy the demands, we need other services that need to be provided. Are you familiar with the term ancillary services? Yes. What is ancillary service? An ancillary service is all the other services that we need to provide to the system in order to help the system operator manage the power system in a reliable manner, which means, imagine that you have this forecast of the demand. Even if you consider different scenarios, you are never going to be perfectly sure about what is going to be the demand. The demand is a random variable, changes continuously. It depends on somebody connects a load or there is a trip and then you lose some some demand from one moment to another. So it's like the system needs to be prepared to deal with all these contingencies. How? Well, providing reserves. For instance, being able to increase your power or decrease it according to some set points established by the system operator, this is a product, this is a reserve. You see what I mean? This is an ancillary service. The generators provide these ancillary services like an insurance. You are there in case the system operator needs you, they will use you. It will use you. And this makes it possible to ensure that in every single moment there is a perfect balance between generation and demand without compromising the security of the system. Is it clear? This is one example of a very basic ancillary service, which is the reserves. upward reserve or downward reserve. What is upward reserve? I mean, if I have a generator with, I don't know, 300 megawatts as maximum power, if I schedule my generator at 285, I'm leaving 15 megawatts as capability to increase my power if necessary. So if everybody is scheduled at its maximum capacity and the demand is higher than expected, no one is able to provide this extra power to satisfy the demands. And the process of starting up one generator takes time, can take several hours. It's something that you cannot do from 1 second to the other. So there are different control loops with different time constants. So we have primary reserve, secondary reserve, tertiary reserve. We have non-spinning reserve. In order to ensure that balance, okay? So we are going to optimize our unit commitment cost, the objective function, but subject to have every hour a minimum available reserves. From the generation perspective, we are going to assume that we have certain input-output curves. This is a typical example that we use. This is the output power, and this function tells me what is the amount of fuel that I need to produce this power. Okay, normally they have, it can be approximated by a quadratic function. In that case, we are going to use a linear approximation. We have beta, which is the intercept with the vertical axis, and a certain slope, which tells me what is the marginal. And then, depending on the price of this fuel, you will have a cost or another. Okay. This is important to remember that depending on where you are operating your thermal power plant, your unitary heat rate may change. Normally, you design the generators to be more efficient, close to the maximum power, where the ratio between the power that you are producing and the amount of fuel that you are consuming is the most efficient one, right? Okay, another important concept. When you are optimizing the unit commitment, one of the most important elements in the total cost structure are the startup costs. Is everybody aware of what does it mean? Startup cost. When you decide to start up, for instance, a combined cycle power plant, you need to incur in the cost of making the power plant ready to be on. So sometimes if the unit has been off for 20 hours, the amount of fuel that you need to burn in order to have the generator ready to produce electricity again is higher than if the unit was off only 3 hours ago. Okay, because the time, the longer you have to wait, the conditions of temperature and pressure in the case of all coal power plants were far from the requirements to be producing electricity optimally. Okay, so normally we distinguish between a startup cost that takes into account the number of hours that the unit has been off. Okay, this, from the optimization point of view, is really challenging because we need to account for how many hours the generator has been off. Okay, this is a variable that needs to be taken into account in the system. Okay, another typical constraint are the ramp constraints. What is that?
How fast the generator can increase.
Exactly. It's like when you are driving. You cannot go from 0 to 100 miles per hour in 1 second. It takes some time when you change your velocity, right? So in the case of a power plant, this is more true for thermal power plants, but also in hydropower plants, you may have also ramps due to other reasons, okay? It's like, for instance, recently we were in a project and the hydro generator is very good because it has no emissions, it's renewable, but it has an impact on the ecosystems that are in the river, okay? So if you are discharging water with your hydropower plant, if you change the outflow of your hydropower plant very rapidly, this creates some bad conditions for the. So sometimes you need to incorporate ramp constraints not only to the thermal power plants but also to the hydropower units in order to limit the maximum change of power between consecutive hours. Okay, there are different type of ramps, but from the optimization point of view, this is very challenging because this links what you do in 1 hour with what you could do in the hour before or the next hour. So you are coupling the different hours, okay? And this is something that the model, the optimization model, has to consider in order to obtain a feasible solution. Is it clear? Questions? Okay. Okay, I'm just giving some, messages. Of course, we could be talking about any of these topics a lot, but the purpose here is to have a general overview. One very common approach when if you read the papers on unit commitment is that they characterize every generator with its own generation function, which means that every generator consumes more or less depending on its own production. Okay, this is not 100% true when you face real data. Why? Because every generator may have its own input-output curve that tells you how much fuel I need to burn in order to produce electricity. But what is the price of this fuel? Well, it depends on how much consumption you have in your utility. So this links the cost function of the different generators, because maybe you have your gas purchases depends on the total volume, and therefore you don't have independent, let's say, costs. You see what I mean? It's like the total cost depends on the combination of the power produced by all the available generators that belong to you. Another example of aspects that link the operation of the different generators are the third-party access to the gas grid, for instance. Imagine that you have several generators that are withdrawing gas from the network, from the gas network, from the pipelines. I mean, the amount of fee, I don't know if you're familiar with the access, the third-party access, is like whenever there is an infrastructure and you want to make use of it, you need to pay like a fee. Like when you go through the highway, you need to pay just to be allowed to use the infrastructure. If you're you have a factory and you consume gas, okay, you pay for the gas, for the molecules, but also you pay for the right of using this infrastructure, right? Well, the power plants are users of this gas infrastructure, and the amount of money that they have to pay depends on the total consumption of gas every day, every month. Well, there are certain fees. This means that the final price that I will have to pay with all my generators will depend on how much gas I have withdrawn at certain nodes of the gas. Okay, if we have several generators placed in the same zone, the final price will depend also on how much of them and how much gas all of them have consumed. Okay, here I have some references where we try to, let's say, formulate from a mathematical point of view what we've learned from the real problems seen in the industry, okay? Because sometimes there are some mismatch between what is in the papers and what you face in reality, okay? Okay, moving on, we have hydro generators. The hydro generators, normally you organize the hydro units in a river, so you have what we call cascaded reservoirs. So if this is a reservoir, the water released by it will reach the downstream reservoirs after several hours. So here, all the reservoirs and all the power plants, some of them are run-of-rivers. They don't have, like this one, for instance. This is a run-of-river power plant because it has no reservoir. All the water that comes has to be turbined and produced. So here you see an example of how the topology of these elements limit very much the flexibility that they can have. I mean, everything is interconnected. In the model that we are going to see here today, we are not going to model all these hydro systems in such a detail. We are going to work with a composite representation, because at the end, what is a hydro generator? if we had to define it in one sentence, would be what? It's a energy constrained generator, which means that, well, I cannot use as much water as I want because the amount of water I have depends on the inflows and depends whether I have a reservoir that stores this energy or not. So it's an energy constrained resource. And what is the cost of this energy? What I mean is that it's clear that with a hydro generator I can produce electricity. And if I want to minimize the total cost to satisfy the demand, I will have at certain moment either I produce it with a, let's say, a combined cycle power plant, or if I use a hydro generator. So how will you make the decision? How can you prefer using water or gas? The cost of the gas is clear because you need to go to the gas market and buy that gas, and you have a price for the megawatt hour that you produce. This is clear. But what about the hydro?
How much water you have in your reservoir? So if you have lots of water, maybe you should.
Exactly. But how do we formalize this concept? The point is that the water has no cost because it's free. I mean, it rains or snow, melting, whatever. You didn't have to pay for the water, but it has a value. The water value, this is another very important concept in power systems because you need somebody who tells you what is the water value that you have stored in your reservoirs in order to decide if the water value is, I don't know, $80 per megawatt hour. If the gas is, I don't know, 100, you will prefer to use the water rather than the gas. But if the water value is 200, you prefer to use the gas rather than the water. And who tells you what is the water value? Somebody who sees what is the impact of using the water now compared to what you can do with it in the future. I mean, when you have a reservoir, you have the ability to decide to use it now or to keep it for the future. And the water value is related to the opportunity cost. What is the cost of the thermal generators that I can substitute with these resources in all the time that I have available for using this resource in my time scope? You see what I mean? It's like if instead of washing, I could decide to use water now. Okay, I'm going to substitute, let's say, some thermal power plants at this cost. But if this water can be kept in my reservoir to be used, I don't know, 3 months later, and in this third month, the demand is very high and you might need to connect even more expensive generators, it's preferable to use this water and so to save it for the future because it has a higher value. You see the point? However, if you have a run-of-river power plant, which means that the water is coming, has to be produced, otherwise it's lost. The water value is zero. I mean, use it now because otherwise you're going to lose it. Okay, you don't want to curtail, you don't want to spill this water because if you don't produce that water, it's energy that you're going to lose, as if you had, for instance, a wind farm. If you don't produce with the wind farm because you curtail that energy, you are losing that. Okay, so this is why we need somebody, somebody who sees the future and tells me what is the water value. Or equivalently, somebody who tells me you have this energy for the current week, which is the way in which we are going to model the hydro resources with the prototype. It's like you have this energy constrained resource and you have to use it through the week in an optimal manner, but don't produce more than this energy that I'm allocating to you for the week. Do you understand the concept? Okay, it's not an infinite resource. Okay, and this connects very well with what Andres will explain. Somebody, I mean, a model that sees the whole year or the next 2 years is the one who sees the impact in the future of every box is a week. So what you do in this week will affect the future, and therefore somebody who sees that future is necessary to tell me how much water I can use in the current week. Okay. Among the mathematical techniques available in the literature, there are many possibilities. Nowadays, the most, let's say, the most preferred technique is the mixed integer linear programming, which is a linear programming model in the form that Pablo explained in the introduction, but where some variables are restricted to take only integer variables. In general, but in practice, in many cases, binary variables, 0 or 1. So you can model a decision like being on or off using a binary variable. And from the optimization point of view, there are, well, different solvers that are able to deal with big problems in a reasonable time, and this is why this is the way in which many, let's say, real models used in the industry are built. I'm going to skip that. Yes, any question? Okay, I think that I have here all the mathematical formulation, but I don't want you I prefer to go to the prototype, and I will explain a couple of the constraints to help you. The purpose of this is to connect what I can do with the mathematical technique involved, okay? But I would like you to start playing with the prototype. And I will come back to this later on. So I have prepared, everybody of you have access to Canvas? No? Okay, I would like you, if you go to Canvas, we have prepared two prototypes. One is written in Python Pyomo, okay, and another one is in GAMS. I'm going to use the first one, so you don't have to install nothing, and I can guide you in the process. Here I have prepared very detailed instructions, so I beg you to follow. Sorry. No problem. So there is a zip file in the unit commitment. So what I invite you to do is to download that zip file and extract all its content into your local directory.
Sorry, I can't succeed. My remote's not working.
Have you downloaded the zip file and extracted all the content? Yeah? Okay, the next step will be to go to Google Colab. So here you have the link. Assume that you have your own, and you may have something like that. So what you have to do is to click on Upload, and from the zip files that you have, the zip file that you have extracted in your local directory, you have to find the file which is called MUC Weekly. It's a Jupyter notebook, and you have to drag it here. Do you need help? You need? Yes, is no, it's here. Prototype, this one. I'm going to show you because maybe I didn't. So I say I arrived just from the airport. I couldn't connect to Canvas. Let me see, Canvas, to show you the. Wow, password. Is it one of them? Okay, so just to be sure that we are in this course, modeling energy systems for a data center. So the one that I would like you to download is, we are here, Tuesday. These are the slides that I'm using. This is the prototype that I want you to extract. So press here, you download it. You see Python pyomo.zip. And copy wherever you want, in a temporal file or wherever. I'm going to do it with you, just in case, in temporal. I'm going to copy here. I'm going to extract it, extract everything. Okay, so this is, I have extracted this zip file into my hard disk. Okay, I'm here. Everybody's at this point? Yes? Now, go to Google Colab again. And it says upload. You upload, and here you can browse or you can drag directly from the working directory this file. So I'm going to drag, sorry. I'm going to drag it here. Okay. So you should obtain something like that. Everybody is at this window? Yes? Okay. So next step, if you go to the instructions, if you get lost, next step would be, we need to upload input files. So we need to click on files and we need to upload. So here we have here files, press here, or click here, sorry, I mean, and then and then here, upload to session storage. Okay. So here. So we are almost done. This will upload to session storage. So what you now have to select is all the files except the main one, okay? So open, okay, and we are done. So if we I don't know how many of you are familiar with Python, with Jupyter. Well, this is a notebook. Well, I'm not an expert, okay? But here, what I mean is that we have different cells, okay, that you can, I'm going to go through them a little bit, because part of what we want to teach you here is, in case you want to develop your own model, to have some examples to start with, okay? The good thing is that here, as you saw, you didn't have to install nothing. You didn't have to install Anaconda or any other software, okay? Here you have, by default, this picture at the end. We need to obtain a different one to make sure that the model has worked. How can I test? Well, I'm going to run all the cells. You know that in a notebook, what you have is a set of different cells that you can run them independently, or you can run all of them. Okay, so press here, run them, run all. Here you said it is executing. If you go up, you will see that it's doing something. Here, I mean, why are we able to run this model without installing anything? Because there is a solver which is called HiX, which is open source, okay, that is available in Google Colab, that is quite powerful. I mean, normally in the models that we develop for industry, we have to pay for licenses like Cplex in the past, nowadays more Gurobi, okay? If you want to optimize problems with, I mean, a realistic number of variables. Of course, you only have a free license, but very limited in terms of the number of variables and constraints that they can deal with, okay? But this is free, and it's quite good for research purposes, and even for doing some, we use this for our classes, basically, okay? Because even here, we are optimizing a whole week, and I'm going to describe now what is the system that we have. It's not so small, so, okay, and I'm going to give you some ideas of, or some information about what is all this, but at the end is the structure of the optimization problem that is solving, and that you see here the process of how this is being optimized, okay? So, whenever you have binary variables, a ver, que sin el ratón no puedo aclarar aquí bien, a ver, no, sí, a ver, okay? Here you can see gap. Well, the point is that when you are optimizing a problem that involves binary variables, in theory, you could reach the optimal solution of that problem, but this might require exploring a very large search tree. So what we normally do is we apply the solver does, apply what is called the branch and cut, which is like a evolution of the branch and bound algorithm, that what does is to explore that search tree with a searching strategy that ensures that you're always improving, but when the solution is good enough, you stop, okay? And how do we tell the model that the solution is good enough? When the tolerance is below a certain threshold. In that case, with a 2% is finishing, okay? And this is important because when you run your models, sometimes if you want to be more precise, you can reduce that tolerance, and this let's say a parameter that you can set according to your preferences. Okay, did you run the model as well, everybody? Tell me if you get at the end something like this. Because the difference between the default picture is that here we have 2 nuclear power plants. Now I'm going to explain what is this. But I want you to, in order to make sure that your model has worked, you should obtain exactly the same figure as mine. Everybody? Yes? Okay. What about here? No? Did you obtain anything, or it just?
Yes.
Did you run all, and you go to the end?
No,
Is it still, what is? Did you? Yes, you upload here. You upload all the files, right?
yeah, all the files.
And you run here all.
And if you execute and
I don't know what is happening.
let me try to do it again.
Because this is the Google account, isn't the same as me, right?
Yes.
Okay, I'm going to continue and we will
Yeah,
come
no
later,
worry,
okay?
no
Okay. Perdona. Okay, let me, well, maybe you can interpret these results. What do we have here? Anybody? Exactly, and how many days we have here? We have a whole week, okay? This is Saturday. This is the shape of the load that we have in Spain. It has been normalized, but this is typically the shape of the demand on Saturday. On Sunday, where the peak load is even, it's typically in the afternoon, in the evening. And then we have Monday, Tuesday, etc., okay? And here, what I'm showing you is what is the solution of the problem. Once that has optimized the total operational cost, here we see 2 nuclear power plants working as a base load, okay? 1 gigawatt of one nuclear power plant, 1 gigawatt of another nuclear power plant. Then we have here some coal power plants, okay? Now we want to decarbonize the sector, right? To reduce emissions. Let's see, now, one thing that I want you to do is, how can we reduce the coal production? In Spain, for instance, coal power plants are no longer in the mix, okay? We are in a very strong transition to more sustainable mix, okay? Now what we have from the thermal point of view, we have here, what you have are the combined cycle power plants. This is what we have now in Spain. We have the thermal generators are basically combined cycle power plants because they have a lower emission rate, and we need them in order to accommodate larger amounts of renewables. Then we have, in green, we have wind, and in this orange or yellow is what you have the solar production, okay? And then in blue, what you have is the hydro production. What you can see here is that the hydro, which is modeled here as an energy constraint resource, where are we using the hydro energy? When is the model preferring to use the energy? It's doing what is called the peak shaving, right? Because it's when allocating the water in these periods is when I am substituting the most expensive thermal generators, okay? Because if I use this energy, I don't know, in the off-peak hours, in these hours I don't have that energy, and therefore this energy should have to be produced by some more expensive generators, okay? Okay. Let's change things. Of course, you could change directly sure.
This is prediction, right?
Yes, it's like somebody told you what is the demand for the whole week.
Know how much solar and how much wind you are going to have for the next week.
Somebody tells you hour by hour what is the maximum wind or the maximum solar production that I may have. It's like the crystal ball is very good. So it tells me what is the demand and what is the irradiation and what is the wind speed. It's a deterministic approach because this is the simplest model that we are going to see in this week. It's like, but even solving that is not obvious, okay? I mean, if you check how many variables, how many, well, it's a hard problem. But yes, it's like here everything is known. But the fact that you have these predictions for wind and for solar, it doesn't mean that you need to produce it always. Sometimes there is more wind and solar than what is needed. And in that case, you need to curtail wind and solar. Because if the demand is no higher, I mean, sometimes you need to curtail. Sometimes it's because network constraints. Sometimes it's because there is no room for all that. Okay? Okay, so what is the cost of this? Well, if you go to the left side here, you can see here a summary of the results. Okay, if you press on this, this is a CVS file that tells you what is the value of the objective function in euros. Okay, what is the total generation cost? What are the total CO2 emissions? What is the CO2 emission cost? Because here we are minimizing the total operational cost, but we are including in the objective function that whenever I produce with a thermal power plant, I need to buy the emissions allowances. And this depends on the carbon price. One of the parameters is the carbon price. So I want you to play a little bit. We have like a few minutes left. You can change the input data and update the resulting, the required input data. Okay, for instance, here you have the wind and solar. We have the data for all the thermal power plants. But we have prepared here, so in order to make it more, let's say, didactical here, we have prepared a cell in this notebook, okay, what is modify parameters. So it's very agile. We can just modify here and see what happens. Okay, let's start by assuming that we have more renewables in the system, okay, which is the default case. You saw how much wind and solar production, and it was, well, was limited, right? It wasn't very big. With this factor, penetration factor, I'm going to assume if I change here the number, what I'm doing is that the hourly data that we have for wind and solar is going to be multiplied by this factor. So for instance, change, what if we had 3 times more renewables than the default case? Do it for me. So here, right here, 3, for instance, or 3 or 2, whatever you want, and see what happens. I'm not going to do, so I keep the default case, okay? Okay, now let me this at least this one. You have remember that you need to run all, okay? Before it finishes, I have downloaded the previous results. Okay, has not finished yet. Depending on how, I mean, the time is not, the time the model requires to solve the problem can change. Things now it's optimal, you see? What is the solution that we have obtained? What do you see? What changes do you see in this figure with respect to the one that we had before? We have much more wind. I mean, we have 3 more time wind and solar than in the default case. So we see here that the model has a lot of more renewables. Okay. What you see here is that the production of the combined cycle power plants and the coal units have been displaced. Okay. This is what we want. We want to reduce fossil fuel generation. But the point is that this solution is taking into account not only an aggregate number in terms of energy that can be substituted. No, it's energy that can be substituted, taking into account that, for instance, this generator is subject to this RAM constraint. It's trying to increase its power, but this solution is accounting for this constraint of this particular generator. You see? Whenever if you shut down this generator, it's going to be off a number of hours before you can start it up again. So it's like when you want to assess what is the impact of having more or less, like in this scenario, more wind or more solar, well, the rest of the system is modeled in a very detailed manner. Okay. What else? What is that? Exactly, this is the pumping storage. So this is the negative production, because when if you have a pumped storage power plant, I mean, if you have a lot of renewables, in many hours you will have an excess of power. Well, this is the good thing for the storage. I mean, in the hours when you have an excess of wind and solar production, you will store that energy. Of course, you're going to have an efficiency that in the case of a hydro pumped storage might be, I don't know, 70%. But then I can use this energy that is in some hours an excess of available energy to be used in the hours where the demand is higher, and this is more optimum. Okay. Questions? Yeah.
Can you talk a little bit about the operational side of this? Like, how often does someone, run this type of model?
These models are run. I mean, my personal experience for the company for which we develop these models, they run not only, I mean, it's not a single model like this one, but they run many instances of this problem. Every day they run several times, and only for 1 week, but even for now that you can run these models in the web, in the cloud, normally we cover up to 2 months, for instance, of hourly, because they need planning. I mean, they need to know how much gas they need to purchase, what are the estimations in the marginal cost, because many market decisions are based on these estimations. What is the impact of having more or less renewables? So they are run every day several times, okay? Okay, let's do another experiment before we finish. We have like 5 extra minutes. There is, in the slides, that I skip all the mathematical, I mean, the snowstorm had to, but I want you to, at least from a mathematical point of view, understand how this equation works, okay? Because we are modeling the startup and shutdown decisions. U is the unit commitment. So U T P means that the generator T in the hour P, if it is 1, it's on. If it is 0, it's off. You see the point? So what if I want to change from off in the periods P minus 1 to be 1 in the next period? So this is imagine that one generator is off in the periods P minus 1 in the before. What if I want to be on in the next period? Physically, what do I need to do in my system to go from off to be on? I need to start up, right? So I'm going to define this Y as the startup decision, which means that when y is equal to 1, it means that in this period I'm starting up the unit. It's a a variable that only takes value 1 when the decision is made. Okay? Normally it's 0, but only when you start up the unit, y will be equal to 1. You see? So if I write this equation, if I want to go from 0 to 1, I just need to add here 1. 1 is equal to 0 plus 1. And if here I subtract set, which is the shutdown decision, I don't do nothing. I don't shut down. So this means that by this constraint, I'm able to model the relationship, the logic between the discrete decisions. U is the unit commitment, Y is the startup decision, and Z is the shutdown decision. What if I want to go from 1 in the previous period to 0? In that case, I need to activate my shutdown decision. Well, this equation is magic. It works because here I don't do anything regarding the startup, but now 0 is equal 1 minus 1. And this, by means of this simple constraint, which is the unit commitment logic constraint, I mean, this is a good example on how we as modelers, by means of one equation, we can model a reality, because at the end, these decisions have a cost. The model automatically, by means of this constraint, learns that if they want to change the status between, the commitment status between 1 hour and the next one, something has to be done regarding the startup or the shutdown decisions, okay? What if the unit is on and in the next hour is on? Well, you don't do anything. You don't start up or you don't shut down. And this is true. And if it is 0 equal to 0, plus 0 minus 0. Somebody might say, yes, but 1 is equal to 1 plus 1 minus 1. It's true. This could be possible. But as a startup and shutdown decisions have a cost, the model will prefer not to activate in the same hour a startup decision plus a shutdown for nothing. Okay? But if you, in case you don't want to have this possibility at all, you can add another constraint saying that the sum of these two binary variables have to be lower than 1. This is one example that at least this constraint I thought that at this point would be interesting. Okay? Okay, so final question. We have 3 minutes before we finish. There is one, excuse me, here. Oh, okay. One of the parameters that we have here is the price of the CO2 that by default is $20 per ton of CO2. Okay? And here you have another parameter that is the maximum number of tons that you allow in the market. I'm not going to do the whole thing because of time constraint, but I want you to run the model if we increase the price of the CO2, okay, to 80. And using the same factor in the wind generation as we had in the first place. So we have a not so renewable system with the penetration factor 1, the same as the first case, okay, but with a more expensive CO2 price. Instead of 20, I'm going to put 80. What do you think is going to happen? What is your guess? Because always when you use these models, and this is maybe the most important thing from this first session, is like you as modelers are not just intended to press the button and believe whatever the model tells you. You always have to have a critical, let's say, sense on the solution. You always have to think of what do you expect, and the model will confirm whether you are right or not. And if what you are obtaining is not what you expected, maybe you were wrong, or maybe the model is wrong. And this is completely necessary because normally these models are so complex that if you just press the button and believe everything, this is going to be, for your research, a very bad strategy. So what do you expect from here? While the model runs, I want you to, here, run all. More hydro? What do you think more hydro? Because the hydro is an input data, the energy that we have for the week. So it cannot create water from nothing.
When you say go from 20 to 80 CO2 costs, what do you mean CO2? So
Yes, in Europe we have the carbon market. So generators, apart from paying for the gas that they are burning in their combined cycle power plants, or for the coal, although in Spain we don't have coal, they have to pay for the emissions that they have. Whenever you produce with an emitter, with a fossil fuel power plant, you emit tons of CO2, and you need to buy the allowances of all these tons in the CO2 market. And therefore, this increases your cost. And this is why we have decreased so much our emissions in Europe, because it was an extra cost. And therefore, the most efficient generators were displaced by the less efficient in terms of emissions. Okay? What is the emissions rate for a coal power plant? It's almost 1 ton per megawatt hour produced, 1.9 tons per megawatt. For a combined cycle power plant, it's 0.4. Okay, it's like less than half of the emissions. And therefore, despite being the price of the coal cheaper in terms of the amount of energy that you have, as you have to pay for the carbon emissions, the merit order changes because of this fact. Okay, this is one of the policies that you can have: create a carbon market. Another possibility would be to set a limit to the total. Okay, what do you see here? This is my last message. Exactly, we have no coal at all in this slide. All the previous gray area that were coal power plants that were emitting more than they have been displaced by, in that case, gas power plants. Okay. Why don't we have more hydro here? Because the energy that we have for the whole week is limited. I mean, the sizes of our reservoirs, our inflows is what we have. Of course, what we are doing is to use this water in the best efficient manner. I mean, I'm using the water in the best manner, but I cannot create more energy than what we have. And we have a final question from the back. You have another question?
Just looking at generation cost also went up. Looking at cost price higher, who's going to pay for generation cost?
Well, the objective function now is higher because whenever you put more restrictions to the problem, you're not going to improve. But the way in which this new objective function is split into the different terms can be a little bit sometimes not so obvious. In reality, what happens is that this extra cost that we have imposed to the power system, at the end, it's always going to be transferred to the final customers. That's for sure. The ones who pay are the final customers. It can be because of the costs. If we have a war and the gas price increases, this is transferred to the final customers. If there is a energy policy that is fostering renewables and this has a cost, well, at the end it's always the case. Okay, yes?
How do you explain the variability of hydro? Like it goes like, so the capacity like between the peak, like in one peak, you see how much capacity you have in hydro. Why, like, is it goes down, then it goes up?
Well, because
it should be like fixed.
no, because
it shouldn't vary that much within one day. Like
no, it can vary very much. But in that case, as we are setting what is the maximum instantaneous power, and we have total energy, there are no, in this very simple modeling of the hydro system, is not modeling any RAM constraint, for instance, or is not modeling a minimum production that you have to comply. In that case, the hydro is modeled in a very simplified manner. You have amount of energy and instantaneous maximum power, and it's using the amount of energy in the most optimal manner, which is this one.
So why did we, within one day, the two peak, you drop the generation of the hydro? We should use more of hydro and less of the gas. Like between the
Here,
yeah, why don't keep.
No,
the-
because here, if I don't use this energy here, where should you use it?
No, I should use more, meaning as much as I used in the.
No, because in that case, you don't have enough energy to use more in that hour.
But you can drop the generation from the gas and use more of the hydro.
You have constraints for the thermal power plants. Okay, the change let's say the ramps affect your capability to use water from one hour to the others. This is why we have this little, you see this little slice here, is because the demand is increasing so much, the generators, the combined cycle power plants have a maximum ramp capability, and they're not able to follow the demand as fast as it is changing. So I need to use water in these hours, despite not being so optimum in the sense of avoiding the cost, but it's the only feasible solution.
That means you use more. You drop the generation of the gas plant in that case. That's why you keep it steady and you compensate with the.
You lose more is because there is no other option that is feasible.
It is fixed, like it's like stagnant. When you reach that maximum stagnant, if you start to drop and you think you compensate with the hydro, you will lose more money.
Yes, exactly. Okay, well, for those of you who were not able to run the model, I can help you in the break, and that's all for me now. I think that we can continue with the schedule.